Hey there, geometry. Let me check my speaker. Yep, we're good. Let's start with lesson 13. So, what fraction? It's our warm-up. Our student task statement says that a circle with radius 24 inches has a sector with a central angle of pi over 3 radians. Okay, so we have a circle. We have a radius. And we have some sector, I don't know, like with some angle that is pi over 3. Let's not do that. Pi over 3. So what fraction of the whole circle is represented by that sector? Well, radians I don't intuitively understand, like off the top of my head very well, but I can put it into degrees and I understand it better. Okay? I understand radians, but I've been using them for a bit longer than you. So let's go ahead and change this into degrees, which we did in previous lessons. So I'm changing it in degrees by multiplying it by 180 over pi, which is an equivalent fraction. 180 over pi is 1, so I can multiply it by 1. Pi's cancel out. 180 over 3 is 60 degrees. Okay, 60 degrees makes better sense to me because a whole circle is 360 degrees. So what fraction of it is that 60 degrees? Well, if I change it here, that fraction reduces to 1/6. So 1/6 of the circle is represented by that sector. And then I can use that information to find the area. Area of the sector is pi r, that's not r, squared times the proportion. I can use 1/6, but I can also use 60 over 360 because that's how we've been doing it in the past. So if I do all this math, my answer is 96 pi inches squared. Okay, it's a good warm-up. So a sector area shortcut. Lynn and Alina are trying to find the area of the shaded sector in the image. Lynn says, we found sector areas when the central angle is given in degrees, but here it's in radians. Should I start by finding the area of the full circle? Alina says, I saw someone using the formula 1/2 r squared theta, where theta is the measure of the angle in radians. R is the radius, but I don't know where it came from. Compare and contrast finding sector areas for central angle measures in degrees and those measured in radians. Okay, so when we're doing degrees, hold on, let me erase this. I just copied that from the work. So I just rewrote those. When we're talking degrees, if I want the area of the sector, I take pi r squared theta, where theta is the measure of the angle in radians, and I divide that, that's degrees, and I divide it by 360, which in the past we have just multiplied it by the central angle, the ratio, the proportion of what's in the central angle. And when we're in radians, we take area equals pi r squared times the central angle, but then we divide that by 2 pi, because 2 pi and 360 are equal. Okay, 360 is a full circle measured in degrees, and 2 pi is a full circle measured in radians. Okay, there has to be more than that. Explain why the formula that Alina saw works. It works because it does. Yep, because it does. Oh, silly me. Sorry. Okay. 1/2 r squared theta, where theta is just the measure of the angle in radians. So if I look at this one, let's look at that one. Duh. If I simplify this formula, those cancel out, and I'm left with 1/2 r squared theta. Okay? It works. There's always a mathematical reason. It just needed to smack me in the forehead a little bit. All right, let's move on. Oh, and then find the area of the sector. So we have area of the sector equals 1/2 radius squared times the central angle, which is 3 pi over 4. All right, let's do some handy dandy math. 12 squared. And then 1/2 times 12 squared times 3 divided by 4. So my area of that sector is 54 pi. And I don't have units, and that's okay. Units squared. All right, good job. An arc length shortcut. So the city of Riverside has 2 straight highways extending out from its town hall located at T. So that's a highway. If I highlighted it, that's a highway, and that's a highway. But I want that to go away now. Ooh, sorry about that. Several roads shaped like circular arcs connect the 2 highways. Exits from one of the highways are shown at points A, B, C, and D. Create a table that shows arc length of the connector roads as a function of radius of the highway. All right, so I just pushed pause and created it. So arc length of the connector roads as a function of the radius of the highway. So the radius I listed first. So 2 miles, 2 plus 4 is 6. And you see that, so 2 miles is the first one. 2 plus 4 is 6. 2 plus 4 plus 5 is 11. Plus 3 is 14. Okay? And then I listed the 3, 9, 16.5, and 21. All right. And then it says plot the points from your table on the coordinate grid and connect them. So 2 and 3 over 2 up 3. Except I'm not in pen mode. Over 2 up 3. This is my radius, and that's my arc length. 6, 9. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. I blinked. I hope I didn't lose anything. My eyes get dry when they stay open to count. 11, 16.5. I've already out of room. This was 6, 7, 8, 9, 10, 11. 16.5 is going to be up there somewhere. Okay, let's just show you the answer. Okay, right there. What's it look like? Okay, it's linear, right? The points should form a line. Yes, write an equation for this line using the variables L and R. So I can calculate slope. Sorry, we'll do it here. So change in L over change in R. We'll just do 9 minus 3 over 6 minus 2. I did 9 minus 3 over 6 minus 2. It's like change in Y over change in X. So that's 6 over 4, which is 3 halves, which is 1.5. That's my slope. And now I can grab any of those points and say, all right, my equation is y equals mx plus b. I don't know what b is. So let's just grab, and it's not y and x, I know, it's r and l. So L equals mr plus b. So let's plug in what we know. I know L is 3, m is 1.5, r is 2, and let's figure out what b is. 1.5 times 2 is 3. B is 0. So my equation is, L equals 1.5R. What does the slope of the line mean in context of the highways and connector roads? That means, so my slope was 1.5. If I go up here and look, that means for every increase, let's see, my slope is, let's just say 3/2. It's not a half. This is my change in L over my change in R. So for every increase of arc length of 3, so arc length times 3, the radius increases by 2. So every rise of 3 of arc length, so every increase, I'm out of paper, increase of L plus 3, we have an increase in R of plus 2. That's what slope means. It's your incremental change. So for every L of plus 3, we have an R of plus 2. The city wants to build a new arc-shaped connector road starting at point E. Okay, A, B, C, D. We need another connector road of E. Which will be an additional 6 miles past exit D. Okay, so if I look at this table here, it's a plus 6, so that's going to be 20. How long will this road be? Well, we know that L equals 1.5 times R. We just did R as 20. So that road will be 30. That arc length, that road will be 30 miles because we used the equation that we found right there. And that's it. Good job.